Hello everyone, this is Purple Munchlax here with a different video today. This video is about the Tesseract, which is a 4-dimensional shape. It's like the 4-dimensional equivalent of a square or a cube. This is a Rubik's Cube, as you should know. It's 3-dimensional. Okay, let me just give you an introduction to the Tesseract first. Okay, this is a piece of white paper, and this is a line. That's a line. I'm not sure if you can see that line. I'm pretty sure you can see that line right there. That's a line. Yeah, that's a line. And then you can draw another identical line here and connect these. It's not very good, but it works. And that there is a bad drawing of a square. Here is a model of a square like that. It's not a very good model, but it works. It has 4 corners. Just write that down. Vertices, meaning corners. 4 edges. Edges. 2, 4. 4, yes. And 2D things. 1. Yeah. I'm also gonna put the line down here. Vertices. 2 and 1D things. 1. It's simple so far. The cube. Draw identical this shape. The identical version of that. It doesn't matter if it intersects. And you connect them. That's also not a very good drawing. But it works. I can build that here now. Like this. This is a good representative of a cube. Because I'm using a 3D object to represent a 3D object. So it's good. It's a cube. It's a cube. Let's write cube here. Here? Yeah, that's fine. Cube. Vertices. 8. 1D edges. How many does it have? 12 is what it has. 2D surfaces. 2D surfaces, it has how many does it have? 6. This is all basic stuff. It's all basic stuff. 3D things. Of course it has 1 being 1 3D thing. Okay. Now for the Tesseract, I'm sure you can guess what it's going to be like. You draw an identical cube. Simply like this, and you connect the 2 cubes. That is a very bad drawing of a Tesseract, so I'm going to show you a 3D model of the Tesseract. It's not going to be very representative because it is a 3D object representing a 4D object. Whoops, don't want that happening. Where did my pencil go? I don't know where my pencil is. Right, let me bring the other piece of my model here. This is a lot messier, as you can see. Oops. I'm not quite sure how this was before. Okay, one of the reasons why it's so messy is because I don't have enough pieces to make a solid version of this. Because of course I don't have all the pieces in the world. I don't have infinite pieces. So I just put this in here and connect these. This is hard work. This is extreme hard work. And I just realized I connected it in the wrong way because the cube is not in the right orientation. Okay, now that this is done, I'm just going to show you this. This is of course two cubes connected together. This might not make sense yet, but I'll try my best to explain it. This can also act as a video that's about, it's like an introduction to 4D. Talking about the simplest 4D shape, of course. This is the simplest 4D shape. Now, I just need to find my pencil. Okay. Alright, anyway, that pencil is now under maintenance. Okay, Tesseract. That's right here. Sorry for the interruptions there. I was interrupted, of course. First pencil is back from maintenance. Tesseract. Vertices, of course. Start with vertices. We can count them, or we can follow the pattern of vertices being 2, 4, 8. This is doubled again, being 2 cubes connected together. 16 vertices. Vertices are 0D. 1D edges. 1D edges. Okay. 1D edges. Okay, if you count the edges, or count it from here, which you can easily count, the 2 cubes, 24, and the 8 connections. 32. There are 32 of these. 32. Okay. This is weird. Ah, yes, of course. Never mind. Yes, 32 is correct. You can count from here if you want. Okay. And we can work out the other ones. 2D surfaces. Well, the thing about this is that the 2D ones are also edges. 2D edges. I'm going to do that. 2D edges. How many are there? This is a harder question because you can't count it as easy, although you can kind of count it. One way to do it is to write some simple equations. For example, by looking at this, you know that every 1D edge is connected to 2 of the 2D bits. I mean 3 of the 2D bits. there are 32 of the 1D bits. So in total, there are 32 times 3 connections. This is called a 1D edge touching a 2D edge, a connection. So we can write a simple equation, and every 2D edge is connected to 4 1D edge. And the final one is what we're looking for. Let's just call this E, because why not? So 32 times 3 is 96 equals 4 times E. So E equals 96 over 4 equals 48 over 2 equals 24. So there are 24 2D edges. This is also countable. This is the edge, this is a 2D thing, this is 2D thing, this is a 2D thing, this is a 2D thing, and this is a 2D thing, this is a 2D thing. Well, you can't count them. You can pause here and count if you want, if you really want to. Alright. Now, 3D surfaces. In the Tesseract, the surfaces are 3-dimensional. And all 4D shapes. Actually, they're all 3-dimensional. And how many are there? You can calculate this using the 1D edges or the 2D ones. I'll demonstrate both, I suppose. I'll do the 2D one first. So, every 2D edge, I'm calling them 2D edges because there's really a name for them, I think. I don't know. This stuff is mostly figured out. I don't know the actual names of any of these things. Okay? So every one of these, let's look at the top one over here because it's simpler to look at. It's connected to 1, this normal looking one, and 2, this strange looking one, this tilted looking one. And is there 3? I don't think there is 3. It's connected to 2. And how many are there? 24. And as you already know, every 3D one, every 3D surface is connected to 6 2D ones. Although, yes it is. Yes. So equals 6 times E. Now let's call it S. Let's call it S. 24 times 2 is of course getting 48. Okay, times S. So S equals 48 over 6. Which equals I don't know, 16 over 2, which equals 8. There are 8 3D surfaces. You can use the same method to calculate with the 1D edge. I suppose I can demonstrate this. You can skip this bit if you want, because it's the same stuff as before. So, 1D edge, there are 32 of them. And how many are they each? How many is each one connected to? Let's take this one at the very end here. This one where my thumb is pointing to. This one. connected to the normal looking one at the top, of course. The tilted looking one that on this side of the thing. And it's also connected to the crazy tilted one that's on this side. So everyone is connected to 3. Is that right? I don't think there's a 4th one that it can connect to. So we'll know if we're wrong later anyways. Every 3D surface is of course connected to 12 of them. So it's 12 times S. 32 times 3 is of course being 96 equals 12 times S. So S equals 96 over 12 equals 48 over 6, which of course equals 8. Once I get 8. Also calculating, you can also use vertices to calculate that. You can also use vertices to calculate this, and you can use vertices to calculate this. Otherwise, not bother. You can try that yourself if you really want to. And of course, for the things. 1. Okay, so we know all this, but how does a 4D shape work? I think the best way to understand how 4D works is to look at the relationship between 2D and 3D. The relationship between 2D and 3D. So, imagine that this is a 2D world. And this is there's a cube behind here. Let's just draw a bad square here. And this square here is a square that this guy here comes across. This guy here comes across this big square. Obviously, in the 2D world, the only thing you can do is go over it. Okay. So the big thing, the most confusing thing here, I believe, is 3D surfaces. How can the whole of this thing be a surface? How? So, the 2D guy is thinking the same thing. He sees this as a surface. This as a surface, and this as a surface. He does not see this thing as a surface. That is inside the material. Just like the middle of this cube is inside the cube. Well, if you turn this a little bit, then this is the new land. The guy is still stuck in this pane. The guy is stuck in this pane, and is unable to leave this pane. You can't move that way or that way. So all that can be a surface. Because there's a cube here. There's a cube here. But of course, if this cube was extending this way, out into, I guess we can call this the foreground, and of course that wouldn't be the surface, that would be the inside. Now, raising this to the 4th dimension, Okay, I'm trying to think of a way to refer to the fourth dimension, like how forward and backwards, like a word for that, for movement in the, or direction in the fourth dimension. Okay, whatever. Okay, this cube. How can all of this cube be a surface? Let's look at how 2D and 3D are different even further. So, imagine this is a plain 2D world, nothing in it. And in the depths, there is a cube moving towards it. Dun, 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 dun. Like this, moving towards it. Dun, 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 dun. And then, there's a guy standing here. He's standing there. He doesn't see anything, of course. Wow, the cube is still moving towards this plane. And then, suddenly, let's draw a guy on here. The guy on here. The cube reaches it. And he sees a square materialize into thin air. As it passes through, I want to show you the 3D view here. Obviously, that guy is stuck in this 2D world and cannot understand how this cube is moving through his thing. He sees the cube materialize, and after the cube is done moving through, the cube disappears. And let's take this piece of paper. The cube disappears, and he's all confused. Okay, now another cube is coming. This time. Okay. Anyways, let's relate that to the fourth dimension. If a Tesseract happens to be moving towards our 3D plane here, it would the whole of the front 3D surface will come at the same time if it is going flat on, like it was in my demonstration. It was going flat on. Then all of the front surface in the Tesseract being 3D will reach this 3D plane at the same time. So a cube, we would see a cube materialize, and as it moves through, it would disappear. Okay, let's think of something else. Now, let's assume that all of this top area and all of the bottom area is blue, although it evidently isn't. Just think of it. And the whole middle thing is green. And this color and this color doesn't matter, because in the 2D world, if it passes through in this direction, the person in the 2D world will never see this area, this surface. Alright, so once again, the cube approaches. So I have to switch to this side so you can see this side. And then the cube comes through, and then the guy sees a blue square. A full blue square. The surface of it. A blue square. And as it moves through, it turns into a green square. And it turns into a blue square again. Before disappearing. The guy is confused and all. Okay. Let's bring that into the fourth dimension. If a Tesseract had stripes like that, and it came, you would see a blue cube, and then it turns into a green cube, and then it turns back into a blue cube before disappearing. I hope you understand that. It's difficult to imagine the fourth dimension without having understood it first. Or getting it, without having gotten it first. And it's quite difficult to get it before getting it. Once you get it, it's great. It's great. Yeah. Okay. So what if the cube? Let's talk about the 2D world first. What if the cube was moving towards the 2D plane at an angle? For instance, let's get this, like this. Then, first, a small triangle would start appearing, and it boom, like this. I'm gonna draw the guy in because it's cooler like that. He sees a triangle, and a triangle appear, boom, like that. Sees a triangle, and as the cube moves further in, the triangle grows bigger and bigger. It changes size. Draw the guy in. Changes size. Oops. As the cube moves through his plane, the triangle is actually bigger than it needs to be. And further in, the shape changes, and it turns into a hexagon. Let's see. At this point, it turned into a hexagon. A hexagon. That guy is really confused. And also this hexagon was really difficult to make. And in this point, the paper doesn't fall out. It's cool. And then it returns to a triangle. This time it's theoretically upside down, and it would be on this side. Ignore the upside down guy. Imagine he's not upside down. No, not like that. Like that. Like this. What? Okay, like this. Shapes are so annoying. Like this, like this. And then the triangle becomes a small triangle. The small triangle once again. Before it disappears. And the guy is left confused again. So, what would a Tesseract look like if it came at a similar angle through the 3D plane? I actually haven't figured it out yet. Let's see. Obviously a shape would appear, but what shape would it be? The logical answer would be tetrahedron, but is it actually a tetrahedron? I don't know if it's complicated. Whatever. Instead of thinking about that, you think about a square that is spinning halfway through the plane. Like, imagine the square is in the middle here, I mean the cube, and it started spinning in a very simple fashion, simply like this. What would the guy see? The guy would see the square when it's facing straight on. When it turns, it will stretch into a rectangle, and then after a while At this point, it starts shrinking back into a square. And it repeats. If a tesseract were to be spinning in one direction in our 3D world, what would it look like? Well, obviously, it would first be a cube when facing straight on. And then it's tough. It's tough. Let's look at our model. Our model that has been sitting here for the whole time. Alright. Okay, let's think of the simplest way first. The simplest method of spinning. When the cube is here, and it spins like this, then the guy would see a rotating square. If the tesseract were here, our cube outlines here. Our cube outlines here, like that. And it spins like this, where both of these normal looking squares spin together at the same time. Of course, being impossible because it's not an actual tesseract. Then we would see a rotating cube looking similar to like this. There are 3 directions the tesseract can spin in that will make it look like a rotating cube in one direction. Of course, it can spin like this, or like this. This cube here can spin in any direction. The other cube will follow it. Let's look at the dimensions of this tesseract. The dimensions. The diameter would be the square, like from one corner to the other square, would be the square root of 4, which is 2. It's exactly 2. Distance from one vertex to the opposite vertex, assuming that the edge length is 1. The diagonal is 2, which makes it interesting, of course. Very interesting. I just realized that my camera stopped recording. I was recently talking about the diagonal length of the tesseract being 2, the diagonal length. A cube of being the square root of 3, which is 1 point some crazy decimal. I am trying to figure out what a tesseract would look like spinning in a direction that would allow us to see it being strange. Okay, I'm terribly sorry, but I can't think about it that, like, immediately. About what it would look like spinning in other directions. And plus, this is just an introductory video to the basics of the Tesseract. Well, so we don't actually have that. There's one thing left I want to say, and I don't think I've actually explained how this whole thing could be a surface, but of course, in the 2D world, see a square if it is at the absolute edge of the 3D shape, the plane, the absolute edge, like if this bit wasn't here, then this would be the surface, then all of it, otherwise it would not be the surface. So if a Tesseract has just touched a 3D world, then all of the cube, including inside, would be on the surface. However, if it moves a bit more, then only the surface here would be the actual surface. And you have to remember that in a Tesseract, this thing here is 3D because there's extra dimension to it, meaning inwards and outwards. Let's say inwards and outwards. To make this also a cube, it would be a cube. That would be a Tesseract. The surface would be a cube. This is 2D, which this extends also. This is 2D, which it extends. On the very edge of a Tesseract, this is the one of the 3D edges, the 3D surfaces. This one 3D surfaces. This would be the actual vertices. These 8 would be 8 of the actual vertices. These would be actual 1D edges. And these would be actual 2D surfaces. 2D edges, I guess. With the whole thing being one surface cube. I hope I made enough sense. If you have any questions to ask, you can ask. And if you want me to say anything more about it, you can also ask. Although I might not be able to answer this because this is all self-thought out this. So see you later. Have a good day. Bye bye.